is the briefing for breakout session 3 of our webinar, and what I'd like you to discuss is the question how harmonization and migration are simplified when we use a small CL4 footprint in the architecture, or when we use the so-called train-centric safety logic. I will give you some hints and some startup for the discussion, but I want you to please assess and collect arguments for and against the argumentation, and to find out if how much or how large the effect of simplification really is. First, again, like in the main presentation, you saw it in the slides in the beginning, what is infracentric, what is train-centric safety logic. The simple, or the most simplest way to understand this is to compare here, or again with a flank protection example, how you check if something is prepared safely for a track usage like a train movement. When you check safety in an infracentric way, you check if the infrastructure is prepared in a safe way. So for flank protection, for example, you check if the point machines are set up in a certain configuration that is by certain rules considered to be safe. So you check infrastructure status. And this is of course the historical way of checking safety, since there were no information about trains online. The only way to check safety is to prepare the infrastructure for a safe usage of the infrastructure. Now with ETCS, of course, we have the train-centric way with level 2, because we have now information about the train and we can control the train or the track usage in general. So when we want to assure that a movement is here safe in terms of flank protection, we use the information that we get from the train. So we know where all trains are, we know what movements they got, and we know that in a certain moment when I want to prolong an MA in a certain way, I will explain that in one of the next slides, I can check how long the distance on the reachable route of the track is to the next danger, like moving train or construction site or possession. So here we check distances of track users, or of track usage, which can also be a construction site. So the safety rule is just based on that. So these are different types or categories of safety rules. And of course, you could combine them, but they have some basic differences in the approach which I would like to sketch. In the infrastructure-centric safety checks, what you do is, and this is something like a binary logic tree, is you check the combination of trackside assets and in combination with the already granted or reserved track usage like routes. So it is combining trackside states. And the rules for the trackside states are quite complex. This is always the case when you have binary trees or decision trees, that they get very large and complex because you have to handle all situations. For example, in Switzerland, our traditional line-side signaling interlockings have some hundreds of such rules because you want to increase efficiency in certain situations. You want to have this type of flank protection or that type of flank protection, or you want to have a dynamic flank protection, and so on and so on. So you get a lot of rules to describe what you want. And this is more the operational way of thinking about safety, because you configure something, a setup, in an operational way, and you have to consider all operational situations that can happen and then allow or not allow such situations. And of course, this is the traditional and operational history. So all these rules are very country specific. Some people call it also interlocking logic or something like that. But they are, of course, quite different in many terms, and they are also quite special for certain national interlocking types. There were tries and attempts to harmonize interlockings on the basis of such operational rules, but these projects failed because it was not possible to align in Europe on the same completely operational safety rules at that time. When we go to train-centric rules, they are just basic and they are just a handful, because here, when we just compare the track usage and build the rules on that, you just get more or less, it's simplified a bit, but you get a handful of small basic rules, because there we go to the safety per se. Safety per se just means things shall not collide, so no collisions, so track usage should not overlap. This is basic. Or, for example, that the speed should be compliant, of course, to the track usage, or that when track usage happens adjacent to each other, that the distance of the track usage should be compliant to the speed of the objects. So if there's this is the overlap discussion, if there's a risk of slipping through the outside of the granted area, that this can be handled. So speed and distance should apply to each other. And of course, points shall not move below train. And of course, trains shall not pass open barriers. So, but this is basic safety. In this basic safety, this is in more or less the target here on the right side that in the past was achieved by having these hundreds of operational safety rules. They just in the end always want to target that the right side is achieved. Now, having train-centric safety rules and to be able to work with them means directly just to write them down and use them for safety checks, because now we have train-centric information. And these are the same in every country. Of course, there might be parameters in such rules, like, for example, overlap lengths and such things, but the rules, the basic structure of this rule is always the same, because it comes from nature. Avoid collisions, separate traffic. So what does it mean, for example, in terms of flank protection, when we say the criteria speed shall match distance or distance shall match speed? How does that work? When you have a situation with two trains here at the top in a train-centric safety check situation, every time somebody wants to prolong his MA or wants to start a movement or whatever, the reachable, on his path, reachable things that he can reach are checked. So what distance do they have? So, for example, if the point is open here and this train is moving in that direction, for example, entering a station, so he cannot reach the other train, so there's no distance risk to be checked. So we have what we call in former times a flank protection situation of configured, but here we just have much simpler rules, because for this train we have just to check, and also for this train, if he wants to prolong his MA, so he gets nearer to the other one, is there any reachable route that he can create a risk or not? If not, then he can use the track speed, which is the physical speed of the track. If the point is close in a way that they can reach each other, then they are a danger for each other. And now in this situation, prolonging an MA means that speed and distance need to follow a safe function, which means they have a relationship to each other. So, for example, if they are very slow, of course, they can get near. And if they are very fast, of course, they cannot get near. So here, and these are parameters you can set up as a configuration parameter. So in the end, for a movement, there's no need to set up a static flank protection or something. All you need to check in terms of safety is what is the reachable path for a movement and what is the distance on that. So you can always, for each situation, each topology, each status of the points, you can always use this simple basic rule to check. Now the TMS, of course, has to think about it, because creating situations like that allow higher speeds, so it can optimize, but it also moves more points. Depending on the distances of the things, it can optimize what it wants to do. If the distance is high, so the other train is far away, of course, you can avoid moving around points for flank protection, but if they are near, they need to do it. So TMS, of course, has the option now here to optimize in terms of capacity, asset usage, and configuration of the status. But the train-centric rule is very trivial and basic and always works. What does it mean in terms of architecture thinking like that? when you see the infracentric architecture, if we would, let's say, theoretically harmonize it, which was tried already, then we have something like a traditional interlocking down here with, of course, RBC and other things, which is a Seal 4 system, and then we have a CTC system sometimes for automatic route setting, which is Seal 0 to Seal 2, depends a little bit on the country. And this would be the area that we want to harmonize, including the interface to the TMS. And then we have typically a no Seal or Seal 0 TMS, which plans, and this is not in the harmonization scope. So when we would harmonize this one, we would try to harmonize all of these hundreds of operational rules, how to set up things. So the history of, for example, flank protection would get lost in each country, and we have to decide for one of them. But it's not only about flank protection. I just use it as an example. There are also many, many other things, for example, how to reserve things, how to handle construction site, how to join a split, prepare for that, and so on. So the history here needs to be harmonized. So it is an intervention on the operational way of doing it. But how is it when we now move the so-called cleanup of the Seal 4 footprint, which means moving all these operational preparations up to the TMS? More precisely said, it is moved up here as a standard version, but also the TMS has the possibility to influence trackside asset states directly and change the configuration of the infrastructure directly. What does it mean? TMS gets a bit larger, interlocking gets smaller, much smaller, because it now just needs to check the basic rules in a train-centric way. So here we have a very small Seal footprint, which is a nice cost reduction, because here, of course, you have the high multiplication. For example, if you have 500 interlockings and 200 execution systems and one TMS, you move here a large functionality from a high factor to a single installation with a no-Seal situation, no-Seal functionality, which is, of course, strong cost reduction and simplification. The other point is, of course, when you are in the Seal 0 or no-Seal area, you have much more possibilities to use technologies that cannot be used in safe systems and can be much more sophisticated. So this is the cost effect. But what about harmonization? Well, this part here is not harmonized. So when we move up the operational thinking up to the TMS, a country can still prepare and set up the flank protection like it wants to do it. It can still have the same way of preparing infrastructure in the way that it is used to it. So it can keep habits, it can keep history, and this in a way where it is completely free. It could even, it's a bit crazy, but it could even set a system up here which has a, for example, Seal 2 or Seal 1 checker that checks flank protection in the old way. If people are crazy enough to do that, they can do everything they want here up here. But anyway, the harmonized system, which has the high multiplication in terms of product and installation, is very simple, generates a safety that is by far okay. It's absolutely no risk. And it does not intervene into the operational prediction, because when the TMS is setting up like this or like that in the country, depending on distance or whatever, the TMS can still do that, can prepare that, because the safety logic in the end will just check if somebody asks for a certain MA prolongation update with certain speeds and certain distances. It just checks, is this allowed or not? Is it safe or not? And that's it. So it does not intervene in the way how infrastructure is controlled. So this here keeps the possibility or freedom, and this makes harmonization simpler, of course, because here people still have a lot of possibilities to have their local way of production, how they want to produce with their infrastructure. And the basic system that is harmonized just guarantees a safety and a high flexibility of usage. So this is the